Okay, good morning, everybody. Good morning, everybody. Welcome to this new episode of Control Systems 1. Before we start, some shameless advertisement. My 30 seconds of please come and see all the live demos, beautiful live demos at the Institute of Dynamic Systems and Controls. We're going to hold our yearly Open Lab Day next Thursday, and you're going to see all sorts of stuff from great labs run by great professors, all robots flying, driving, doing all sorts of fun things. So there's even free food at the end. There is no reason you shouldn't come. So, done with the advertisement, let's get back to business. What is the status of our exploration of control systems? In the previous classes, we have understood how it is important to describe this relationship between inputs and output signals of various systems, right? So we defined our linear time invariant systems. We understood, we told ourselves that we're only going to deal with causal systems and only single input, single output systems. So we cranked through the math and we saw, well, look, there's these inputs, there's these outputs, there's these state variables that kind of make the connection, bridge the connection between inputs and outputs. And we understood that given some initial conditions, we could write the evolution of the state and the evolution of the output according to some formulation. And we started analyzing which bits and pieces of this output response were and how they behaved and how they were related to the properties of the system. So we saw that, generally speaking, the output can be written as a term that depends on the initial conditions and the free response, and a term that depends on the input, which represents the way the input affects the system state variables and therefore the output. And we first analyzed the term that depended on the initial condition, and we said, look, this is always going to be a sum of exponentials, complex exponentials. So it could be sine waves, it could be just exponentials increasing and decreasing. It's very important for stability because we define stability as in different ways, but the bottom line is, well, if you send a finite input to the system, you'll get a finite output. So every time you have the output of your system that is growing unboundedly, like an exponential, it means it's unstable. So we said, look, we can tell stability of a system by just looking at the eigenvalues of the A matrix. In particular, if we were writing it in continuous time, we could say, look, the eigenvalues of the A matrix have to be such that their real parts are negative because they appear as exponents of these exponential terms. Therefore, if you have a negative exponent, things converge. But then we had to deal with the other part of the output, which was this messy integral. And we said, well, how in the world are we going to understand? How can we generalize something? How can we get some intuition on the relationship between the input and the output, right? So we did some magic. We chose out of the hat a special input, E at the ST, plugged it in, and we saw that we could get a relationship that we called the transfer function, which is a relationship that regulates the input and the output at steady state in some domain, in some complex frequency domain, which we later learned that was the actual Laplace domain. So, well, why did we do this? Why did we just exchange a known evil for an unknown evil? Typically, that's not a good idea, right? We had our messy time domain equation. Why did we exchange it with a messy frequency domain equation? I mean, well, how does that make any sense? The sense comes from the fact that transfer functions, even in the most general forms, can be expressed as ratios of polynomials. And fundamentally, as we will learn today better and more as we go forward, they make our life easy. They bridge the gap between studying LTI systems in the time domain and actually designing controllers to achieve specific information, specific specifications like stability, performance, robustness, and so on. So transfer functions, although it might require a little bit of somewhat a leap of faith because they're very general things, they actually make our life easy. So let's take this as an assumption and we'll see how it works going forward. So we talked about continuous time systems. And we saw how the transfer function, again, the transfer function is the relationship between the output at steady state and an input to the system, could be expressed by this form, right, where C, B, D are all parameters of the system. We didn't explicitly derive it, but this holds for discrete time systems as well. So there is no big difference there. So once we convinced ourselves that transfer functions were actually something worth investing some of our time in, we said, okay, let's look at what's the messiest situation, what's the most general case, right? So in the most general case, a transfer function for single input, single output systems, remember that the transfer function is a relationship between the input and the output. It's the map in the frequency domain between the input and the output to a system, right? So we said we're studying, just because we decided to do so, not because it's some limitation from above, that we're studying single input, single output systems, which means U is a single input and there is a single output. So a G of S is a one by one, it's a number, okay? This will not be the case, for example, when you'll take control systems too. If you'll take it, you will study multi-input, multi-output systems. So the transfer function actually becomes a matrix of transfer functions. But everything we study here will apply to the most, let's say, more complicated situations as well. Of course, there are some extra little nuisances to take care of. So the transfer function is a number. It's just you plug in a specific S, you get a complex number. And this is the most general way you can express it. Fundamentally, it's a ratio of polynomials. Look at how easy the math is, right? This is high school math, and it's used to describe completely this tool that is one of the most powerful things ever, because you can apply it from aerospace engineering to the shower in the bathroom to anything that changes in time, okay? To economic models, to finance investments, to chemical reactions, to whatever, basically, whatever process can be described by ordinary differential equations, and it's linear. So, okay, this is nice because it gives us some confidence. It says, well, look, even the messiest case doesn't really look like something too fancy. But we said, okay, so it's clear to us how we can go from a linear time invariant system that is x dot equals ax plus bu and y equals to cx plus du to a transfer function, right? We derived the equation, c times si minus a inverse b. But how do you do the opposite? What if I give you a transfer function and I say, classical exam question, can you find a realization, a minimal realization for this transfer function, right? So basically, if you recall, when we introduced these state variables or LTI systems, we said, look, the choice of state variable is not unique. Like these state variables represent a way to keep memory of what happened in the past, right? So depending on the physical situation that the equations describe, there are many different representations. So when you do the inverse passage, when you go from a transfer function back to a system, so given a transfer function, I want you to find A, B, C, D, there's choices to make, right? So choices to make to restrict from the many different choices of state variables to the ones that you actually want to realize. So we introduced this concept of observability and controllability, and we said, look, it's really nice if we had a system that was both controllable and observable. Why? Because, well, then we can actually control it. The inputs can actually reach, affect, change all the state variables. And it's observable means, well, from the output, we can actually reconstruct the state variables. So there are nice systems that we can manipulate and we can kind of tell everything about if we look at the signals that are available to us. So by making these kind of assumptions, we can create special realizations. And this was the controllable one. So if you're given a transfer function in this form, well, you can just follow this pattern. You put the coefficients of the denominator at the last line of A, a big identity matrix in the top right quadrant, and a bunch of zeros. And this is a system that matches the transfer function above. If you don't trust me, and you shouldn't, just do the math. Take these, do C times Si minus A inverse B plus D, and see that it actually turns out to be the same. And this has the beautiful thing that it's controllable, right? So if you put it in this form, you're sure that the model you're making for the system is controllable. But there are other ways we can write a transfer function, right? So the most general way, the just ratio of polynomials, is interesting, but not necessarily the most useful way to write this transfer function. And useful really depends on what we want to do with it, right? So since we understood that these transfer functions are critical instruments to describe the relationship, the effect of input signals on the outputs, well, then probably they're going to be very important to help us both analyze and synthesize, both analyze behaviors of systems, of interconnections of systems in particular, and synthesize controllers. So actually come up with procedures to design a controller to meet specifications. So there's three, let's say, these are some interesting representations of transfer functions. They're all equivalent. You can just jump, this is just the mathematical way you write it out. The first one, it's called the partial fraction expansion. And it's nice because it breaks down the transfer function to its fundamental elementary components. We saw when we studied, remember that, sorry if I take a parenthesis here. X dot equals AX plus BU, state space representation, time domain for linear time invariant systems, is totally equivalent to a transfer function in the sense that there are simply different ways to describe the same thing, which is a relationship between two signals, okay? So when we see G of S here, it's not that it's a different thing with respect to the system we're studying. Give me a state space representation, ABCD, give me a transfer function, we're talking about the same thing. So everything we learned about ABCD somewhat needs to show up here as well because we're just describing the same thing in two different ways, right? So if you remember, we did a class on modal coordinates. We said, look, there's a special transformation that you can do, a change of coordinate of your state variables that diagonalizes your A matrix. Not always, but in the simplest case. Well, if we diagonalize the A matrix, we can show then that the free response is given by just sum of modes, right? And the modes are governed in time by the eigenvalues of A. So we had these terms that were A, E at the lambda IT, right? And depending on how many lambdas we had. So this is the way to express the transfer function to see that. Each one of these terms represents the contribution coming from one of the eigenvalues, because we will see that these numbers at the denominator, the values of S that are roots to the denominator of the transfer function are called poles of a system, very important. And the other side, the numbers of S that are solutions, or roots, are zeros for the numerator of the transfer function are called zeros of a system. So the poles of the systems are actually the eigenvalues of the A matrix. So, okay, so this is a nice way to write things down because it breaks down the contribution of each of the modes. If you have all eigenvalues in your system, but one that are stable, well, you write like this, you find immediately which one is the unstable one. So what about another form? This is what we will play around with today in particular, the root locus form. So this is just a different factorialization. All you do is you take your transfer function, you find what the roots of the numerator and denominator are, you find the poles and the zeros, and you re-express the polynomial as a product of its solutions. So no magic here, just rearranging the terms. In this form, well, we can expressly see the poles and the zeros, while in the previous form, we could see the poles very well, but we didn't see the zeros explicitly. We had these r's at the numerator, these weights for each one of the modes, and those are called the residuals. So, okay, this is a form we'll look at today a little bit better. And what more? Then there's the Bode form. The Bode form is something that we will talk about in a few classes from now, but it's basically the most convenient way to show graphically what the magnitude and the phase of the transfer function are. So this might seem arbitrary, but remember, every time you deal with a complex number, we just said transfer functions at the end of the day for every S are a complex number, it should automatically trigger in your brain, well, complex number means I need to study magnitudes and phases because complex numbers are just defined like that. So the Bode form is the best way to look at magnitude and phases of transfer functions. The root locus, as we will see today, is a very nice, easy way to sketch out what the behavior of your system looks like. We'll get into details of this later. And the partial fraction expansion is a way to look at the individual terms better. So, okay, now we said we we looked at the denominator of the transfer function, and he said, look, the values of S, the poles of the transfer function, are the eigenvalues of the A matrix. Okay, that's a straightforward connection. What about the zeros of the system, of the transfer function? What are they? How do they affect their response? Where do they come from? So to build up in that direction, we started saying, okay, look, let's define some common responses of the system that are typically used to see, to evaluate like the performance, the transient performance of the response. And we said, okay, we look at the impulse response. So what's the impulse response of a system? It's just the response of the system when you send an impulse as an input, and the impulse is a delta of Dirac. So if we suppose that the initial conditions of the system are 0, so the first term here goes to 0. Well, this is the general output of a system. If you plug in delta of Dirac, and you remember the delta of Dirac properties, so actually, let's just write it like this. You will see that the impulse response basically is calculated by putting this tau equals to 0 and has this form here, which, by the way, it's the same form as an initial condition of the free response when the initial condition is equal to B. So, okay, so what's the impulse response? If you just poke the system with an imaginary super fast poke, that's how the system responds in time. And we will see that the impulse response is actually very important. It's as important as the transfer function. It actually is the transfer function. It's just that it's represented in the time domain, and it's the inverse Laplace transformation of the transfer function. What about the step response? So the step response is a very common signal that is used a very common, let's say, response that is used to evaluate the performance of the system in the transient. So basically, all it says is, what if we send to a system a constant input, a 1, okay? And we just keep it at 1 for every time bigger than 0. And we'll see how the output of a system tends to that constant value, right? And so sending, how do we derive the step response? Well, let's just send as an input a 1 and evaluate the output from the general solution. So a 1 can be expressed as E at the 0t, right? And so we know that the solution, if we send the steady state output, if we send a signal of E at the st, is given by G of S. So if we plug a 0 here, we know that the step response is basically G of 0. And so if we just do the math, this is the general equation of the output. We're just saying that U of t is equal to 1, so it doesn't show up here. And well, what's the solution of that integral? If the inverse of A exists, it's just given by this term here. Okay, so these are two important quantities to keep in mind. Now, if we have a first order system, like a scalar system, first order means, well, remember, the order of the system is how many state variables you have, right? So if you write it as x dot equals ax plus bu, the order of the system is n, where x belongs to Rn. It's basically how big the x vector is. So suppose you have a scalar system that is x dot equals ax plus bu is just a number. We can say that basically this term E at the AT just becomes a E at the AT. It's no longer a matrix, it's just a number, so we can pull it out of these matrix multiplications, and we get our steady state response, a step response that basically depends on the steady state one. It's basically saying, look, if this is the situation here, we send 1 as the input, the steady state response might be this one, and we just grow in this way like this. This would be a first order system, maybe like this if A is smaller, maybe like this if A is bigger. What if instead we have a higher order system? Well, higher order systems, we have to look at the output a little bit more carefully. And that's where the partial fraction expansion representation of the transfer function comes in handy. Because we see that at the end of the day, we can break it down, the output, as a sum of different terms. And each term is given by one of these partial fractions. And basically, Well, we can see that the output is going to be given by a sum of modes. This is something we knew from before. And each mode is governed in time by the Pn, which is the pole of the transfer function, right? And but each of these terms is weighted by these residuals. So while we do understand what the effect of the poles are, well, those are there's no magic, it's just an exponential, right? So plug a positive number at the exponent, what do you get? Something that grows in time. It's bad, instability. So what if we plug a 0 at the poles? Well, you get 0t, it's a 1, so you get some constant term. What if you plug a negative number? Well, it gets convergent. So it's a good sign because it means the output converges to something. The system is stable. But so the poles are clear, but the zeros are not. Well, it might not take too much intuition to understand that if it's not one, it's the other, right? So if the poles affect the E terms, the zeros must affect the residuals that effectively are weights on the different terms, right? Imagine one of these residuals being 0.001 and this other residual being 100. Well, what this means is that in the output, one would see the effect of the second term much more than the effect of the first one, right? So, okay, let's pretend that we are studying one of these terms, okay? Ri s minus pi, and we'll say that pi is a pole of the system. What's the pole of the system? Well, it's a complex number, right? So in general, we can write it as sigma I plus j omega I. So depending on where the pole is in the complex plane, how does that output term look like? So we saw this before, but it's maybe convenient to do it again. Okay, so this is the imaginary plane. Let's suppose we are, I don't know, here. Let's start here. So what does this mean? It means we have a pole that has an imaginary component of 0 and a real part of sigma I, and sigma I is bigger than 0, right? Because this is 0. So what does it mean? It means that if we go and analyze the time domain term that comes out from that piece of the partial fraction expansion, remember that the impulse response is going to be given by the sum of these terms. So let's just look at one at a time. If we understand how one works, then we understand them all. Well, how do you expect this to be? Well, if this is time and this is the ith output, well, we will have a term of the kind Ri e at the pit. So if p is real and it's bigger than 0, suppose this is Ri, well, it's probably going to do something like that, right? It's going to grow in time. It's e at a positive number t. What if you get a bigger positive number? So this is sigma that is much bigger than the one before. Well, you would always get the same thing, just that it's going to probably grow much faster, right? Because you have even a bigger positive number at the exponent. What if instead we are here at 0? So p is equal to 0 fundamentally. Well, 0 means that you always start from Ri. Actually, start from Ri at the 0t, which is a complex way. No, complex is the wrong term here. It's a funny way of writing 1. So, well, in this case, this is just going to be constant, right? Because it's e at the 0t is a constant, so Ri remains constant in time. What if we are at this value of sigma here that is always real, but it's smaller than 0? Well, I guess you understood by now what's going to happen. You start here, and it's going to converge, go to 0 with some dynamics. What if you have a sigma that's much smaller than 0? Well, basically what you'll get is an even faster, so this is a faster convergence if we go in this direction, and in this direction you're going to have a faster divergence, right? Okay, so this is how each individual term will behave if you change the real part. Does this make any sense? Comments, questions, or doubts? You can raise your hand. Okay. So now let's look at what happens, for example, if we're here. Okay, so remember, every time you have a complex pole, you'll probably have, you'll have the complex and the complex conjugate as well. So suppose that we are here. What does this mean? That p is equal to some j omega, right? No real part. So if you remember, when E at the j omega is equal to what? Euler equations, it's equal to cosine of omega plus j sine of omega, right? So basically, all it really needs to ring, the bell it needs to be rang is that the complex exponential is a sinusoid. It's oscillations, all right? And if we have E at the sigma plus j omega t, well, what you get is a term, today my E's and my sigmas are the same, E at the sigma t times this oscillation here, right? So basically, when you have a complex exponential, you get oscillations that are in an envelope that is defined by the real term, the real part of the pole. So in this case, the real part, sigma, is 0. Well, 0, we know what it is. It's a constant, right? So the envelope of this oscillatory response is constant. It means you'll get something like this. What if instead we have a pole that is here? So what does it mean? It means we have a sigma plus j omega. In this case, the sigma is bigger than 0, right? We are in the top right corner of our plane. Well, this means that we will have, as in the previous case, the envelope is going to be some diverging exponential. So you'll have diverging exponentials like this, but the response is going to be an oscillations that is contained between these. So it's a very bad and common thing. These are like, it starts oscillating, but it's growing and it will diverge, okay? It's not a good sign. What if we go in this other place of the complex plane? So suppose we have a pole here. What does it mean? It means this is always sigma plus j omega. And the sigma in this case is smaller than 0. So it means that the envelope is going to be converging. So the response is going to be something like this. This is another very common response you get from real system. It's a damped oscillatory response. What if instead we move towards this direction? So we make always sigma smaller and smaller. Well, here you will have a much faster, let's say this should converge to 0. You have a much faster convergence. So the system might do something like this, for example. Okay, it's always oscillating, but it's converging super fast to the x-axis. So you always, maybe you see just the first part of the oscillation. Okay, so this basically helps us understand if we break down the transfer function in these elementary terms, each one of these terms, depending on the pole, will be one of these things in time. What's the output of the system? Well, just sum up all the terms like this, okay? Each one has a different pole, which is the eigenvalue of the A matrix. So the question now becomes, how do we figure out the zeros, right? Because we always say, all these start from Ri, but what's Ri, right? We didn't really look at how to derive it. We have an intuition that it might depend on the zeros, but so there's different ways to find out what the residuals are. An easy one is just, well, suppose we give you G of S is equal 1 over S plus 1, S plus 2, whatever, okay? And you're asked to write this in the partial fraction expansion representation. So basically, you have to write it in the form A over S plus 1 plus B over S plus 2. Well, one way of doing it, which is the manual way and works always, no fancy recipes that you need to keep in mind, it's just, well, impose this form and then go back and match the coefficients. So this, you can rewrite it at S plus 1 times S plus 2, and you just do the proper math. So the numerator now is that becomes what? It becomes A plus B times S plus 2A plus B over S plus 1 times S plus 2, right? Well, if this was your original form, and this is the one you obtained by putting back together to transfer the coefficients of the partial fractions, well, then all you have to do is match the numerator here with the numerator down there. Here, what is the numerator of your original transfer function? It's 1. What is 1? 1 is basically saying 0s plus 1, right? And here instead you have a plus bs plus 2a plus b. Oh no. So how do you find the a's and b's, so the residuals of your partial fraction expansion? Well, you just set a plus b to be equal to the coefficient of the original one, which is 0, and 2a plus b to be equal to 1. So this is the general way you can always do it. It's just break it down as you want, put it back together, and compare the coefficients with what you had to start with. Another way, it's the so-called cover-up way, and it's basically a convenient way to find the residuals. And what you have to do is just multiply the transfer function by the pole of which you want to find the residual, and send s to that pole value. So for example, in this case, let's say you have g of s is always equal to the same thing as before, 1 over s plus 1 times s plus 2. Suppose we want to write it as a over s plus 1 plus b over s plus 2. How do we find a? We just do the limit for s that tends to the pole, so minus 1, and of what? Of s plus 1 times g of s. So this is basically, it's a fancy way of saying just get rid of the pole, because of course you can't send s equals to the pole, otherwise the transfer function goes to infinity. It's a 0 of the denominator, right? So this becomes a limit for s that goes to minus 1 of 1 over s plus 2. Just plug in minus 1 there, you get the value of the residual. Of course, this cover-up method, this equation you see there, it works, it's nice. It's not comprehensive in the sense we are not covering many cases. What if you have repeated eigenvalues, for example? So there's a nice external resource you can check out to see all the passages in the most complex way. It's not going to be part of your exam, but it's good to look out. Okay, so let's look at what happens. Suppose we have this example. We got a transfer function that somehow gets broken down to those, that has those poles, right? So so what are the poles? S plus 1, the pole, remember, is the 0 of the denominator of the transfer function. So any value of s that makes either of these terms equal to 0, is a pole of the transfer function, because the whole denominator would be equal to 0. So 1 is equal to s minus 1, and here it is. We have this graphical convention, poles are represented with crosses, and the other two are complex poles that are one here and one there. Okay, if we use the cover-up method to find the different residuals, R1, R2, R3, so you will get 1 minus 1/2 minus 1/2. Suppose we want to do it just for one of these terms, so although we did it already, how do we find R1, right? This is R1, this is R2, this is R3. How do you find R1? R1 is going to be the limit for s that tends to P1. In this case, the pole is 1, so the term is s plus 1, so the pole is minus 1, of s plus 1 times g of s. So this is equal to, just plug in s equals minus 1 to this term here. So what happens? Well, s plus 1 minus 1, this goes to 0, and you find out that this goes to 0, this goes to 0. You've got 1 over minus j squared, which is a complicated way of saying 1, okay? So if you do the same thing with the other two poles, you just get the numerators. Very nice. How does this help us? Well, now that you know the poles and the residuals, you know everything there is to know about the time response, because the time response associated to each one of those terms is going to be it's going to be what? It's going to be Ri e at the Pit, right? So we know we have 3 terms, 3 residuals, 3 modes. You just sum them up together, and here it is. This was characterized by having a real and negative eigenvalue pole. So it's an exponential that converges, like we just saw. The other 2 are complex. The complex stuff always sum it up together because they're complex but conjugate. So if you sum them together, the imaginary part goes away. And you get this term here. Oh, sorry, you get this term here. If you combine them together, here is the impulse response of y, the yellow line, in time. Done. Solved the system. If you get a system that has that transfer function, you poke it with a delta of Dirac, what's going to be the output? It's going to be the impulse response. It's just the sum of each one of the individual terms. Calculate one at a time, calculate the residuals, and you've got the response. Okay, nice. Gives us some confidence. But really, we're going about this path to find out what is the effect of zeros, not because we understood the effect of poles, we have not understood the effect of zeros yet. So what we're going to do is basically add a zero now, and we're going to add it very, very close to a pole. So basically, the zero is going to be the same as the pole, the first pole, s plus 1, plus epsilon, where epsilon is a small number, okay? Let's see what happens. If you redo the cover up method and find the residuals, what you'll see is that instead of having a 1 as residual of the first mode, now you have the epsilon, which is the distance between this 0 and this pole. So what does it mean? The residuals are the weights of the modes, right? Epsilon is a very small number. So basically, it means that the 0 has affected, nearly removed, the contribution of this term from the output. If we go and plot them out, now this is epsilon e at the P1t, and P1 was -1. You see that the contribution that comes from that first term, the one characterized by the real eigenvalue, it's basically 0 now. Why? Because we put a 0 of the transfer function very close to that pole. You can imagine a 0 of a transfer function as if it were a filter, a dynamic filter. It cancels out that contribution of the specific pole. But in general, zeros are just something that changes the residual of your modes. So it changes how much each one of the natural modes of the system contribute to your output. And what happened with the other two modes? Well, the other two, of course, the presence of this 0 changed not only this residual, but even the other ones. So now this is the response. It changed. Can we gain a little bit more of intuition instead of doing the calculations and understand, okay, but what's the effect of poles, right? More in general. So first, this is like a very, very important lesson for life that we're gonna do today, and you remember for all your existence as a control engineer. The bottom line is never, ever, ever design a controller that cancels out an unstable pole and an unstable 0. So don't do 0 pole cancellations. And the reason is the following. Suppose you have a transfer function like this, okay? So before we said, well, let's put a 0 that is very close to a pole, right? And we saw what the effect was. Suppose that now epsilon is actually 0, okay? So we're putting a 0 that matches exactly a pole. Well, what's gonna happen? This good old math, you just simplify them, right? You just cancel out. So your system is going to be regulated by that, described by that transfer function. But really, what you're saying is that the term that was contributing that pole has a weight that is 0. Remember that when we wrote, so this is the transfer function, which is C times Si minus A inverse B plus D, okay? Which, whatever, we'll put equal to 0. So if you recall, when we showed the modal response, suppose that A is diagonal, then this would be C1 up to Cn, then times some diagonal matrix. Then the residual is Ci/Bi. So if you have a residual that is 0, if you cancel out a pole of a system by designing a controller that has a 0 that matches exactly that pole, you're not removing it. It's always there. Systems are always systems. But you're not seeing it anymore. Ci/Bi equal to 0, it means that either Ci is equal to 0 or Bi is equal to 0, one of the two. And that means that that specific mode, through this cancellation, magically just became either uncontrollable or unobservable or both. So having an uncontrollable pole means that now whatever input you send to the system, there's nothing you can do about it. So you cannot touch it, you cannot change it, you cannot modify that part of the evolution of the system. So that is typically a very bad thing, because if that uncontrollable mode is unstable, it means there's no way you're going to stabilize your system, so you're done, basically, it's finished. If it's already stable, you're lucky enough that it's naturally stable, well, you can't still change the performance. You can't make it go faster to 0. You can make it go, have a good rejection of disturbances, performances, and stuff like this. So the general rule is avoid unstable pole zero cancellations. If the pole is stable, well, you can cancel it out. It's going to be still unobservable, but not a big deal. If you cancel out an unstable pole, you are going to have problems because it didn't really go away. It's just that you can't see it anymore, basically. So in order to generalize this concept a little bit more and understand really what are the challenges introduced by zeros, let's look at a few famous transfer functions. So what if we look at a simple integrator, a system that all it does is integrates whatever comes in, okay? So if we just we consider U to be at the ST, which was the method we used to find what the transfer functions were in the general case. The output is, by definition of the system, the integral of the input. Well, what you get is that it can be expressed in this way. So fundamentally, the transfer function associated to an integral action is 1 over s. This is so famous, it's so common that sometimes when you use computer programs, like the symbol for integration is 1 over s, s to the minus 1. That means just do the integral, okay? What if instead we do it for a derivation? Let's suppose we have a system that the output is just the derivative of the input. Well, same approach. If you just put u equals e at the st, you do the derivative. This is s e at the st. Means that the transfer function of a differentiator is just an s. And in fact, it kind of makes sense. Now, like the derivative is the inverse action, the inverse operator of the integral, right? They cancel each other out. And s and 1 over s are the inverse of each other. They cancel each other out. So there is a connection there, right? So, okay, this brings us to a critical point. What is the effect of a zero in general? What does it mean to add a zero to the transfer function, or having zeros in a transfer function? Suppose you have a regular transfer function, that is multiplied by a zero, okay? So suppose that y tilde is the impulse response that would be associated to the transfer function without zeros, whatever that is. So we're just trying to study here what's the effect of the zero itself. Well, you can just rewrite it like this, right? So suppose that, y of t now is the impulse response of the system with the zero, and y tilde is the impulse response of the system without the zero. Well, you can see from here that if you find what is the contribution of each one of these terms, well, the contribution, z is just a number in this case. It's the position of the zero. It could be 3, 10, or a complex number. You get this, so the contribution from this term would be just whatever it was, the impulse response associated to that transfer function. But when you do the inverse transformation of this, s times something, as we've just seen, s times something just really means it's frequency domain code for derivative, okay? So doing this term here contributes something that is the derivative of what it would have been without the s, the derivative of y. So every time you add a zero, what you're doing is you're including a term in the output that is the derivative of the output, which is kind of nice. In general, a derivative is something that predicts the future, has an anticipatory effect, but we'll see that it can even be very bad. And we'll talk about it after the break. Okay, here we are. As somebody pointed out very correctly, we had a typo in one of the slides. When we talk about differentiators, hence the transfer function of a derivative is not of an integral, right? Actually, this is even wrong. Hence, the transfer function of a derivator is s, okay? Are we all set? Was it a good break? Yeah, maybe? No? Whatever. Sorry. Okay, so what is the effect of a zero? A zero in the transfer function introduces a derivative action in the response. Introduces in the output of a system the derivative of the output itself. Why? Because S is the transfer function of a derivator. Now, let's go back to the two systems we looked at before. In one, we had 1 over S plus 1 over S minus P1, let's call it P2, S minus P2 star. I don't remember P1 and P2, but this is what it looked like, okay? Now, in the other one, we introduced a zero. We said, well, let's put a zero in epsilon, okay? And what does it mean? Well, it means two things. First, we filtered out, we canceled out, we attenuated the mode corresponding to that zero. We placed the zero very, very close to the pole. So this term goes away. And then in the output, we added a derivative of the output itself, a component coming from the derivative. So if you notice, it has an anticipatory effect in the sense that the output now kind of grows before in time. And if you notice, if the yellow how do you call it, line here, was the output, well, the new yellow line, which is the new output, is the output plus the derivative of the output. It grows zero at the beginning, it grows very much immediately, here you go. So this big rise comes from the fact that by including a zero, we're actually literally adding to the response the derivative of this output as well. So zeros mean including in the, adding a zero to a transfer function means including in the output a derivative term. It could be weighted by the presence a derivative term, which generally speaking means it has an anticipatory effect. Now, very important thing and often mysterious thing. People are like, what the hell are non-minimum phase zeros, right? This is something you might want to write down. So we know, I hope, you are confident with the idea by now that having a pole of the system that has a positive real part is a bad thing. It's like having a positive, it is having a positive real part of an eigenvalue of the system, which means bad news, instability, because one of the modes is going to grow unboundedly. What about if we have a zero that has a positive real part? Does that make our life, does that mean anything? Is it as bad as having an unstable pole? Well, so if we said that the derivative of a zero that has a negative real part is something that introduces an anticipatory effect, by introducing a zero on the right-hand plane, that is the right-hand plane of the imaginary plane, so it means that the real part is bigger than zero, what we're doing is we are adding a term to the output that is the derivative, but in the opposite direction of where it should be going. So it's weird. It's something that is called a non-minimum phase zero. It's typically bad news in control systems. It's typically one of the biggest challenges is dealing with non-minimum phase zeros. And what we are saying is that instead of adding whatever was before plus the derivative of whatever it was before, we're basically adding minus the derivative. So you get in the response, what's the negative, the opposite of anticipation? An anticipation, but in the wrong direction. So your system typically tends to start evolving in the opposite direction as where the input is given. A good example of this is when you're fishing. You have your fishing rod, right? Suppose you are holding the fishing rod and you model it as a system where you apply a torque at the bottom, right? Because you're throwing your thing. And you take as an output the position of the tip of your fishing rod. Well, at the beginning, if you give an input in this direction, you're trying to what's the verb, to throw the whatever that is, the tip of the fishing rod is going to move in the opposite direction first because it's flexible, right? So you'll give a motion like this, the tip is going to go backwards, and then it's going to spin forward. That's a non-minimum phase system. The output for a time, for a transient time, not forever, but just at the beginning, goes in the opposite direction of your input. Imagine this when it happens to, say, governments doing financial reforms, economic reforms for a country. Suppose that the dynamics of those changes are characterized by non-minimum phase dynamics. What does it mean? It means you do some changes because you want the economy to grow, but maybe in the first 5 years it's going to respond in the opposite direction. So, well, you better know that it's a non-minimum phase thing. Otherwise, you're going to change your strategy. All you have to do is wait because it's normal. It's a non-minimum phase zero. It goes in the opposite direction and then it comes back up, okay? So non-minimum phase zeros are typically a nuisance. And as we'll see even later today, there's very good reasons for which one doesn't want to have non-minimum phase zeros in the system. Any questions? Because, yes, no? No. Okay, so now let's wrap up this part. And let's move on. We said we finally finished the analysis of transfer functions. Basically, we understood they're a way to represent relationships between inputs and outputs. They're made up of poles and zeros. Poles tell us everything there is to know about stability. Zeros have an effect of weighting the different contributions from each mode. And if you have non-minimum phase zeros, you are in trouble, in the sense that, of course, it's a nuisance. It's complicated, not good news. Okay, now let's step it a little bit forward, and let's talk a little bit about controls. What we're going to do is we're going to go towards, we want to study the root locus. The root locus is one of the 3 big methods we talked about at the beginning that helps us understand how the poles of a transfer function change as a function of something that we'll see soon. So we understood poles tells us about convergence, divergence, about stability. Suppose that, so we looked at the response of a few of these systems, right? Like, for example, this, or whatever, one of the previous examples. It would be nice if we had a graphical representation of how the poles change, for example, as we try to control the system in some way. So let's get this a little bit more precisely done. So, very important thing. We get back to our feedback connections. We talked about this a little bit a while back. We know that feedback is a good thing because it's a way for our let's say control strategy to take into account what is actually going on, because we feed back a measurement of the output of the system, and through a feedback action, as we showed, it is possible to affect the dynamics of the system. So if you have an unstable system, through feedback control, you can make it stable. And you can get it to have better performance and things like this. So let's look at this. This is a very common feedback control loop. Things to notice. What's R? R is the reference signal. What's Y? Y is the output signal. What is U? U is the input signal. Input to what? To the P of S. Why is it P? Because it's conventionally called the plant, what you want to control. We use sometimes G, sometimes P, sometimes you'll find H, whatever. It's the relationship between the input and the output. It's the transfer function describing the relationship between the input and the output. Typically, you'll hear it called plant or system, sometimes process. Okay, it's what you want to control. And then there's C of S. What's C of S? This is the controller. So this is what we need to design. We need to come up with a transfer function for the controller such that you get whatever you want. What is the whatever we want? For example, we want E, which is R minus Y, to go to 0 as time grows. We want our output to track our reference signal. Why? Because by definition, the reference signal was what you would like your output to be. So it's a choice of the control engineer, or it comes from some bigger strategic consideration that determines that I would like this system to have a certain performance, which means tracking, for example, a certain reference signal. So the C of S will have the first objective to make sure that Y goes to R. That means r minus y goes to 0. This is called typically the error or the tracking error. We want the error signal to go to 0. So let's do this calculation for once. I'll do it at the blackboard because it's a calculation you want to become familiar with. Because we'll do it over and over in the future. So we have can you see back there? No. We have a reference signal. Better? Note, this is important. Every time we do feedback loops, it's actually a negative feedback loop. Okay? We get this error signal. We send the error signal inside a controller. The controller produces what will become the input signal to our plant, which produces an output signal. We measure the output signal. We feed it back to the beginning. We compare our output signal to our reference signal. Reference is where you want to go. Y is where you actually are. The error is the difference. So how bad are we doing or how good are we doing? E is a quantification of this situation. What's the distance between R and Y? And it's the input to the C of S, which is based. So the controller is some logic, some strategy that tells us, okay, based on what the current situation is and how bad I'm doing with respect to what I would like to do, what should I do? What should we do? What is the action? So we want to try and relate what the output and so note, I'm removing the time variable because I wrote the systems as P of S to C of S, or transfer functions. So to avoid confusion, this would be Y of S. It would be the frequency domain representation of Y, but it doesn't really matter. So we understood transfer functions are just a way for us to describe systems. So we use transfer functions to say this is a system characterized by this dynamics. And then the signals that come in and out, you can imagine them as time domain signals or frequency domain. So what's my point here? I want to find what's the Y of t. So let's say Y is equal to what? It's equal to P times U. Okay? But what is U? U is equal to C times E. Nope. E. Okay? What is E? E is R minus Y. Right? So this is what? So I'll just drop the S, just be for sake of simplicity. It's PCR minus PCY. We've got Y equal to blah, blah, blah. This is stuff here. Take this term and bring it to the other side. What do we get? We get 1 plus PCY is equal to PCR. Left multiply, in this case we don't really care, but what you get is Y equals to what? PC, 1 plus PC. Ta-da! Very important relationship. This is the transfer function between the reference signal and the output. It's as if we have just put our whole feedback operation inside a box, which is a new system, and we called it, how do we call it? Well, you know how we're going to call it? We're going to call it T of S, and we'll tell you later why. So now this is T of S. It's the relationship between the reference signal and the output of our system once we hook up a negative feedback control structure. So, okay, why is this relevant? Because now we're going to look at a few things. So note how there's the open loop branch, which is the one that goes from E to I. It's the top part of the feedback control loop. And we will say that the transfer function P of S times C of S is, we'll call it the loop transfer function, the open loop transfer function, L, okay? And it's the product of your controller times your plant. We just saw that the Y is equal to PC over 1 plus PC. This is what we just derived at the board, okay? So PC is L, we just defined it to be this way, and this is L as well, so we call this whole thing T of S, which is L over 1 plus L. These are definitions, okay? Don't worry if you, just take it as a definition. What is T of S? T of S is the closed loop transfer function. The name kind of says it all, but you need to think about it because it's easy to get confused while you're in the middle of an exam, for example, between open loop transfer function and closed loop transfer function. But if you think about it a little bit, they're obviously very different. The open loop transfer function does not have a feedback action. It's the direct relationship between, imagine E as the input to the system. The system is now the product of the two transfer functions. This is one of the things we did, I think, in class 1. We did, what's the interconnection of different systems? And we saw if we had a series of two systems, the operator was just the product of the two, the composition of the two. In this case, it's just the product of the transfer functions. The closed loop transfer function is what happens once you feed back the output. So you have this much more complicated dynamics that is described, that is related to the open loop transfer function in this way here. Open loop transfer function divided by 1 plus open loop transfer function. T has the name of complementary sensitivity function. Why? We need to introduce the stuff that is not the point of the situation now, so we will talk about it. So just get it as good. T is the complementary sensitivity, and it describes the relationship between R and Y. As a consequence of that, we define the sensitivity function, S, which is 1 over 1 plus L. What is the sensitivity function? The sensitivity function is the transfer function between the R and E. So, of course, these are all signals. R, E, U, Y, the output, the reference, the input. These are all signals. They all change in time. Well, we focus on the output because that's what we see, what we measure, what we would like to behave in a certain way. All the others are signals as well. And a transfer function is a way to describe a system. What did we say a system is? It's just a mapping between two signals. So you can pick any of two of your favorite signals inside this control loop, and there's going to be a transfer function between those two signals. The ones we care about typically most are reference to output, maybe reference to input, maybe noise to input, maybe disturbance to error. Things like we can pick and choose any two signals, and we'll find a transfer function that relates those two signals. And the way you actually find it is by doing a calculation exactly like this. You start from what you care, and you go backwards until you get the one you like. But for the moment, let's just focus on T and S. And so remember, let the words help you. Why they're called sensitivity and complementary sensitivity? Well, because if you sum them up, you get L over 1 plus L plus 1 over 1 plus L, which is 1 for all S. This means that the complementary sensitivity and the sensitivity function, at every point in frequency, they sum up to 1. There's a constraint. You can't just do it, you can't arbitrarily design one and the other. If you touch one, you're touching the other. And this is going to become one of a big theme going forward, because because fundamentally, as we will say in a few slides, sensitivity and complementary sensitivity describe what we want to change as control engineers, describe the relationship between the reference signal and the output. We would like, for example, to achieve good tracking, perfect tracking, we would like this whole transfer function to be equal to 1 at every frequency. Why? If we design the controller C such that that transfer function is equal to 1, what does it mean? By doing the feedback control, at every point in time, the output is going to be exactly equal to the reference. Perfect tracking, right? We want to engineer the complementary sensitivity function by choosing C of S. The sensitivity function is instead the transfer function between the reference and the error. Well, maybe we would like that sensitivity function to be stable. It means in time it converges to 0. Why? Because it then means that that E goes to 0. So the Y tends to the R, which again is what we would like to do. So anyways, we will look at these things a little bit more in detail. The general idea is that there are constraints between the different sensitivity functions. So unfortunately, we cannot arbitrarily design each one of them. If we touch one, you kind of have the other one. It's like a rope. If you pull one end, the other one gets away, right? So we have to do trade-offs. Before we proceed, we said that the transfer function between Y and R is d1, d2 over 1 plus d1, d2, right? So suppose d1 and d2 are constants. Forget about the s's. There is a denominator here. You want d1, d2 to be different than -1, okay? So there are some situations like you want to have your feedback loop to be well-posed. And well-posedness comes from the idea that, well, for example, you would like these two values not to be such that at every point in frequency you've got zeros at the denominator of the transfer function, otherwise we couldn't even write it down and it's not well-posed, okay? This is just something we have to say for let's say, completeness. But another more important concern that stems from what we saw 5 slides ago when we looked about zero pole cancellation is that now we're designing a controller, a C of S, right? The C of S comes before the P of S. It's very tempting to say, look, I've got an unstable pole on my system, on my plant that I want to control. Let's just make a controller that has exactly in the frequency domain that a 0 at the position of the unstable pole, so they cancel out, and we've controlled the system. It doesn't show up in the math anymore. So if you do that operation of zero pole cancellation, as we've said before, what you're doing is you're just making unobservable or uncontrollable that specific pole. And so the general idea here is that we care about stability, right? We said this before. Is the first objective of control engineering is to make a system stable. And we said, look, there's two kinds of stability. There's the input-output stability, which is what we are tempted to focus only on. And this other thing about the stability of the internal signals, like the input or the error, we'll call internal stability. The idea is that system has to be internally stable as well as in order for external stability to even be something we care about. What does it mean? You could have take for example, a plant that is characterized by this dynamics, okay? So it has a non-minimum phase of 0 and it has why is it a non-minimum phase 0? Because S equals to +1 is the value that makes that 0, so it's on the right-hand plane. And we say, okay, we don't like non-minimum phase zeros because we get this delay in the answer, blah, blah, blah. So we'll just make a control system that is like this. But the control system that has this transfer function has an unstable pole, basically, right? So if you just look at input-output stability, if you just look at the complementary sensitivity function, you'll get that the complementary sensitivity function is stable, but the closed loop transfer function from the reference to the input is not. what's the bottom line? The bottom line is that you might find that if you focus only on one of the transfer functions in the system, for example, input to output, that the system looks stable. But for example, there's one of the signals and other signals inside the system that is growing unboundedly. In this case, you get a stable output, but your input signal is unstable. This means that you would require an infinite control action in order to achieve that stability, which is, you don't see it if you just focus on input-output stability, but still is a big problem. There's no such thing as infinite control action. You cannot have every signal inside the closed loop control thing has to be bounded, okay? So the concept of internal stability means that you just go on, if you pick any two signals in your closed loop control, the reference, the input, the error, the output, we'll see later on, we'll add more signals to make it more realistic. All those transfer functions need to be stable. None of the signals inside the loop needs to grow. So one very good way to achieve this for the systems we're studying is don't ever do pole zero cancellation with non-minimum phase zeros and unstable poles. Now, so having taken these two issues out of the way, what we want to do is make sure that we design C such that the transfer function between our reference to output is stable, T is stable. So what we want is that, how do we find something is stable? We've got a transfer function. Now forget about what it relates. Transfer functions as poles and zeros. We said the poles are what determines stability. What does it mean to have a transfer function stable? It means all the poles must have a negative real part. Okay, so how do we go about doing that? Which is a big question that we'll ask ourselves a lot, and we'll develop many tools to see, okay, now given a system, how do I come up with a C of S such that the closed loop transfer function, T of S, is stable? That means has poles, that is the zeros of the denominator, that have a negative real part. Basically, one could do the calculations, right? One could say, okay, well, this is complex numbers. Complex numbers are messy, but they're just numbers. So let's put C of S equal to whatever equation, crank through the math, write down the closed loop transfer function, look at the denominator, find the poles, solve, and that's the way. Sure, it works. But it's messy, and there are much easier ways. So one can summarize fundamentally all the classical control, all the loop shaping techniques into the idea of let's exploit the knowledge of the open loop transfer function, that is C times P. Why? Because P is given, C we design it, so it's kind of the easiest thing in the world. Now, P is the plant you want to control, C is what you want to design, so you know it by definition. How do we exploit the properties of the open loop transfer function L to find the properties of the closed loop transfer function T? Starting from what we know, L, just P times C, how can we reason only on that, but derive conclusions for the closed loop transfer function, which is what we actually, it's what's going to govern the mechanism of the dynamics of the closed loop. Possibly we want to do this with the minimal amount of effort. Imagine that the first people that did these things didn't have computers, didn't have calculators, whatever. So they had like pencil, paper, and maybe a ruler, okay? So there are three big families of ways to do this. Remember, all we want to do, these are three ways to exploit L, open loop information, to derive conclusions on closed loop transfer functions easily, simply, with graphical methods. Three ways. Root locus, think about it today. Bode plots and Nyquist plots. Bode plots is going to be the argument of the next class. Nyquist plots is going to be the arguments in 2 classes from now. So next 3 classes, all we're going to do is look at easy ways to focus on the open loop transfer function to derive conclusions on the stability of the closed loop transfer function. What's the root locus? The root locus is, so I'm not going to tell you what it is exactly because we're going to talk about it soon, but the idea is that it's used for a qualitative assessment of the stability of the closed loop system. It's not meant to be precise, but it's easy, dirty, and quick. It gives us good insight of what is going on, and it's easy to write down. It has as a backside that it's difficult to represent uncertainty. So if you recall, we said control systems first do stability, then do performance, then do robustness. What is robustness? Like the advanced thing. Robustness is what if the model I assumed of the plant was wrong? So I designed a controller to work for a certain plant, but really the plant was different. It had some variation. It's like there was model uncertainty. So when we say uncertainty, what we mean is model uncertainty. So the root locus is not really the best tool to represent that. What are Bode plots? Bode plots are a graphical way to represent magnitude and phase of transfer function. They're nice, easy to draw. We will look at them, and they are good to do sophisticated designs. They're easy, they're good to represent uncertainty, and they have some positive traits right there. But it's let's say they might lead to misleading results if you don't do proper assumptions. The Nyquist plots are kind of the favorite and least favorite thing of all. Everybody that studies control systems, or at least for me, because it's very powerful. Like Nyquist plots are, you will use them in advanced controls as well as simple controls. They're really powerful. They're somewhat messy and counterintuitive to derive and to represent. But they're really good for representing uncertainty, and they're really powerful as a tool to not only describe stability of closed-loop transfer functions, but even to design controllers. So what's the root locus? The root locus is what we're going to focus on today, and it is a way to represent graphically the position of the poles of the closed-loop transfer function on the imaginary plane as we change the control action. So suppose we are choosing the simplest possible of control actions. So we're saying our C of S is equal to a constant, K. So the logic we choose to control our system is proportional to what? To the error signal. So what we're saying is, well, make it a constant. So the bigger the error is, the further away Y is from the reference, the bigger the control action is going to be. The smaller, the smaller. Is this the best way of doing it? Probably not, but it definitely makes sense, right? So let's suppose that we are doing a proportional control, so we suppose the C is equal to K. Now we want to study what is the position of the closed loop transfer function poles as we vary K. As we change our controller knob, how does the closed loop dynamics change? Can we look at it in an easy way? So we'll proceed like this. So, well, this is the open loop transfer function, right? It's K. This is probably a very bad notation choice. Let's call this P. We called it before, P. So Kp is now, can be expressed like, so we said that in the most general possible way, a transfer function is just a ratio of polynomials, right? So numerator divided by a denominator. So let's just write it in that way. Why? Because it's going to make sense. So, and recall that that we could express numerator and denominator as the product of the zeros on the poles, right? That's how zeros on poles are defined, are values of S that make either the denominator or the numerator, or the denominator equal to 0. Now, what's the sensitivity function? The sensitivity function is 1 over 1 plus KL, right? Because that's how we defined it. And if we represent this, in this case, is P again. So if we represent P as the ratio of a numerator with respect to a denominator, what we get from here is 1 over 1 plus K, numerator over denominator. So all we do is 1 plus D of S plus K N of S over D of S. So look at this. This is very important. The poles of the poles of the closed loop transfer function are the zeros of this equation here. Correct? The poles are defined as the values of S that make the denominator of a transfer function go to 0. The closed loop transfer function between Y and E is, between R and E is S. S has this denominator, which by the way is the same denominator of T. You can do it. You can do the math and check it out. So what are the closed loop poles? The closed loop poles are the values of S such that the denominator of S equal to 0. What's the root locus? Is the graphical representation of this equation here. All the values of S that make this equation be equal to 0 as we vary K. Why is it important? Because, well, if we have a drawing of where all the poles are going to be as we change K, we can choose K to determine what the performance of the system are. We just synthesized a controller. Very simple one. We just said, well, our controller is just K, but you found the number of K that makes your system be stable, for example. How we go about doing that? So we have to start. So this is a little tour de force that we're going to do now in the next 10 minutes. We're going to do a bunch of observations that are really insightful. Some will show intuitively. Some are, the math is a little bit too involved. We will not do it. But you'll trust me, and we'll get to a list of rules. And I gave you pointers to go and double check the math, because you shouldn't trust me. And then we'll use those rules to build root locuses, which are very powerful, which are very simple rules. We'll have an approach that allow us to write down very complicated things, the root locus for very complicated transfer functions. So first, observation. So the first question is, okay, we want to put these closed loop poles where we want, right? The poles of the closed loop transfer function. How many are they? Like, one could have the question, if we put a controller, can we just reduce the number of poles? Because we saw that the response of a system is given by the sum of a bunch of terms. Each one is regulated by one of the poles. So the denominator of the closed loop transfer function is d plus kn, which means it has the same degree of d. And d is the denominator of the open loop transfer function of the plant. Now, and the open loop transfer function was the C of S times P of S. In this case, we're saying it's K times numerator over denominator. So the denominator of the open loop transfer function is this term here. So it means that the number of closed loop poles are the same as the number of the open loop poles. You're not changing the number of poles, okay? That's that. Now, is this clear? Questions, doubts? Please complain if you don't agree with one of these rules, because otherwise you have to follow them. You have to follow them anyways, even if you don't agree, but if you don't agree, we can talk about it at least. So what happens if K goes to 0? Well, let's look at the denominator here of the closed loop transfer function. If K tends to 0, well, then this part tends to go to 0. So it means that the denominator of the closed loop transfer function tends to what? To the denominator of the open loop transfer function. I know it's kind of a game of words, it looks like, but this means that the poles of the closed loop transfer function, which is what we care to engineer, tend, as K goes to 0, to the poles of the open loop transfer function. Why? Because ds plus k, d plus kn just becomes d, and d is the denominator of the open loop transfer function. So remember, a very important rule. As K goes to 0, your poles will go to, your closed loop poles will go towards your open loop poles. What if K goes to infinity? Well, if K goes to infinity, then if we have the same number of poles and zeros, so the same degree at the numerator and the denominator of the transfer function, then we can look from this equation that if K goes to infinity, this part will go away, so the closed loop transfer function will basically be the open loop, will become the open loop numerator. So this means that as K goes to infinity, the poles of the closed loop transfer function tend to the zeros of your open loop transfer function. Ta-da! What happens if you have a non-minimum phase 0? A 0 in the right-hand plane. Close the loop. You crank up your control. What you're doing is you're sending the poles of the closed loop transfer function right into the unstable region. Every time you have a non-minimum phase 0, you can't crank up the gain of your proportional controller or you'll send your system unstable. Bad news, non-minimum phase zeros. If the degree of D and N are not the same instead, we will see that basically what happens is that all the excess poles will go to infinity, and we will go in the details of that later. So, okay, 3 important things. Same number of closed loop poles and open loop poles. K goes to zeros, our closed loop poles go to the open loop poles. If K goes to infinity, our closed loop poles go either to the zeros, actually go to the zeros of the open loop system, and the excess ones go to infinity. Other important thing, the closed loop poles, well, so the root locus, which is just a description of how these closed loop poles evolve, has to be symmetric with respect to the imaginary axis, because the equation that it comes from has real coefficients. So there's no other solution. Okay, now, so we said that the root locus, it's all about this equation here. So you better keep this in mind. It's all the values of S such that that thing goes to 0. The denominator of the closed loop transfer function goes to 0. Let's rewrite this in this way here. Now, remember, easy peasy. Transfer functions are what? Complex numbers. Looks like such a messy thing, but it's just a complex number. And we know everything about complex numbers. What do we know? We know they have magnitudes and phases. Every time you deal with a complex number, first thing, study magnitudes and phases separately. So what's the phase of this complex number n over d? Well, we know that n can be expressed in the root locus form as s minus the first 0, blah, 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 s minus the mth 0, right? So the phase of a ratio of polynomials is the sum of the phases of the numerator minus the sum of the phases of the denominator, if we write it like this in the root locus form. So the angle rule tells us, since this is a complex relationship and it holds because there is an equal, it means it has to hold both for the magnitudes and for the phases. So from that one equation, we can get 2 constraints. The first one, we call it the angle rule, which means that the sum of the phases contributed by each one of the zeros minus the sum of all the phases contributed by all of the poles have to be equal to the phase of the right-hand side. Now, K is a real number. It's a controller. It's like the gain of the controller, okay? So a positive number has phase 0. A positive real number has phase 0. A negative real number has phase 180 degrees, right? Remember the complex plane. If either you're here or you're here. If it's positive, the phase is 0. If it's negative, the phase is minus 180 degrees. So that's where this comes from. So this is very important, the angle rule. It's basically the single most important rule going forward. Then there's the magnitude rule. Comes always from this equation here. Just take the magnitudes on left and right of the equation. What you get, that the product of all the magnitudes of the zeros and so this relation here holds, okay? And this is straightforward application of properties of complex numbers. Now, let's look a little bit at the angle rule in detail because it's critical. What does it say? It says the sum of all the phases contributed by the 0 minus the sum of all the phases contributed by the poles is something we'll figure out next time.